Hello everyone. In this video, we will be solving few questions on Leibniz test. Before we solve questions, let's have a quick look on the statement of Leibniz test. So if in the alternating series this un, you know how to represent alternating series? This is the representation, okay? Now, this series should follow this two condition, then only it will get convergent. So what is the first condition? That un plus 1 term has to be less than and equal to un. And second condition, it should approaches to 0 when n tends to infinity. Then only the series will get convergent. Alright. Now in the previous video, I have completely proved the proof part of this Leibniz test. If you haven't watched yet, it's high time you should watch it. Okay, I will put the link in the description box. You can go there and watch it. Now let's start to solve some questions. I'm starting with a very easy question, the basic question. You know how to represent alternating series. So let us denote the given series by n tends to from 1 to infinity minus 1 to the power n minus 1 and un. This is the representation for alternating series. Now you have to write the nth term. So the nth term is simply 1 by n. In place of un, actually, I'm not writing it here ki minus 1 to the power n minus 1. That I will manage afterwards. Let's go very basic. Okay. Un plus 1 is this. I have to check the conditions. Okay. First condition is that this term has to be less than this term. Alright. So how to check it? So usually n plus 1 term is greater than nth term. It is usually, generally, okay? It's a general concept that n plus 1 term will definitely be greater than nth term. Alright? So if I reciprocal it, the simply inequality will be changed. This inequality gets changed. So first condition is un plus 1 is less than un for all n is satisfied. Now the second condition, I have to check the limit. If limit n tends to infinity, un is equal to 1 upon n. If I put here infinity, I will get 0. So here second condition is also satisfied. This means that this series is what? Convergent. Therefore by Leibniz test, so both you have to write it in a very phrasal manner that both the conditions are satisfied. Hence by Leibniz test we can write that the given series is convergent. So this is convergent. Okay, that's the start of the basic one. Let's move to the higher one. Let us consider the given series. You have to write that line. So actually n from 1 to infinity minus 1 to the power n minus 1 un. Now what is un here? So un is, let's see the pattern. I'm not having 1 in the first term, so it must be n plus 1, and here it is following n. So this is un. So what will be un plus 1? Just add 1 extra to this. You'll get un plus 1. Or you can simply write, because it looks quite difficult to solve. You can even write it in the form of this. Okay, 1 plus n by n plus 1 by n. Alright. Now we know that n plus 1 is greater than n, but the reciprocal of this is not the same. Alright. And if we add 1 on both the sides, I think it does not affect the result. Okay, so from this we can say that un plus 1 is less than un. So first for all n, so first condition is satisfied. Just ignore my writing. Okay, first condition is satisfied. Now the second condition, check. I'm putting limit n tends to infinity in un. Now n plus 1 by n, let's take n common here. So 1 by n I left with this. And if you put infinity, it will goes to 0. I'll be left with 1. Now here comes 1. So this is not following the second condition of the Leibniz test. This means that not convergent. Not convergent, why? Because this is second condition is unsatisfied. Already you have to write the statements why it is not convergent. Okay, so yeah, here is the third question. So this is the un, this is the un plus 1, and root n is less than root n plus 1, so the reciprocal will be greater than. So this shows that un is greater than or equal to un plus 1 for all n. This shows that the series is monotonically decreasing. So first condition is satisfied. Second condition, put limit n tends to infinity here. You will get 0. Second condition is also satisfied. Okay, so this is convergent by Leibniz test. This can be written, this is alternating series, this can be written as minus 1 to the power n. Okay, now this is n actually, so I have to show that n plus 1 is actually, this is greater than n. You agree or not? So here un plus 1 is greater than un. So it is increasing, monotonically increasing. So this is not going to be convergent. So this is divergent because the first condition is unsatisfied. So this is divergent. Okay. Now I am taking the last question of this video, and that is very important. Very important. And this type of question, let's first look into the question. So question is, you have to check it is convergent or divergent by Leibniz test. Okay, this question. Now this form, this is actually n, this form. Okay, you have to check for the convergency of this. All right, limit n tends to infinity. Now if I separate this, I can separate this, no? This type of question can be separated. And if you remember Cauchy's second theorem on limits, if you remember or not, I don't know, but it was there कि n to the power 1 by n. I'm just directly writing it. I'm not giving you time to think, but अगर click कर गया दिमाग में, then hats off to you. Click कर जाना चाहिए. So n to the power 1 upon n is can be written as an plus 1 by an, limit n tends to infinity. So yeah, we limit n tends to infinity. This is what Cauchy's second theorem on limit. All right, and this is also known as I think Dedekind, no not Dedekind, what I was एक और नाम से इसे जाना जाता है. आई थिंक अभी मुझे याद नहीं आ रहा है, बट अभी मुझे कॉची सेकेंड थ्योरम ऑन लिमिट ही याद आ रहा है, तो ये वही है. ठीक है, सो मैं इसको यहाँ इस्तेमाल कर सकती हूँ. सो हियर n प्लस 1 अपॉन n माइनस 1. नाउ दिस, इसको अगर आप लिमिट लगाओगे, लिमिट n टेंड्स टू इन्फिनिटी, इफ यू पुट हियर, सो दिस विल बिकम 1. यू नो हाउ, n कॉमन लेकर, एंड दिस इज अगेन 1 and this is 0. 1 minus 1 0. So I am getting 0. So it's convergent. I think you have enough knowledge by now, by this time of the video, that how to solve the Leibniz test, how to check the following points which are necessary for the convergency of the Leibniz test. So I think this is a good time to stop the video. You can go and solve so many types of questions, whatever book you have just to go and solve. Okay, bye bye.